Hello, this is Jack Jackson, and I'm back with the solutions to some of the review problems that I gave you in the last video. So hopefully you work these on your own and you're just checking your solutions now. So the first one is, what is the average value of f of x equals secant square of x on the interval from 0 to pi over 4? To find the average value of a function, you integrate that function over the interval, and then you multiply by 1 over the length of the interval. So you're multiplying by 1 over pi over 4 minus 0. That's 1 over pi over 4, which is really 4 over pi. And then we're integrating from 0 to pi over 4 secant square of x. Secant square of x is the derivative of tangent of x. So tangent of x is an antiderivative. And then we just evaluate that from 0 to pi over 4. So that's tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. And so the answer is 4 over pi, which we can get approximately in our calculators as 1.2432. Here I did it on a TI Inspire and found the exact value to be 4 over pi and then approximated it there. Oh, that's a typo. 2732. Let's fix that. Okay, there we go. Oops. Now, if you visualize this, here is the function secant square over that interval from 0 to pi over 4. Pi over 4 is just a little bit more than 3/4 there. And the area under that curve is going to be the same as the area under a rectangle, where that rectangle has a height that is the average value of that function. And so the height of this rectangle, the height of that little red bar across the top, is 4 over pi, or about 1.27, which you can see there on the graph. The next one, we have a definite integral. We're going to use the fundamental theorem of calculus to evaluate that, just like we did the last one. We're going to find an antiderivative, but this is a little more complicated looking function. We're going to try substitution. So we see the more complicated base here with a constant power. Let's let that be u and see if that will work out. So if u is 3x to the 5th plus 7, du is the derivative of that times dx. So that would be 15x to the 4th plus 0 times dx. So 15x to the 4th dx. So if I could get 15x to the 4th dx here, that all together would become du. And then the hope is this becomes u to the negative 4. Well, it sort of works out. We've got the x to the 4th and the dx okay. We need the 15 here. We put a 1/15th out front. We also bring the 5 out front. 5 times 1/15th is 1/3. So if we were to distribute the 1/3 in here and rearrange things, it would be the same as the original. We're going to think of this as being a negative 4 power. So when I do my substitution, this becomes u to the negative 4, and this becomes du. We still have our 1/3 out front. Now, if you left this as 0 to 2 right here, that would be incorrect, because the 0 to 2 would indicate u values. So there's two options at this point. You can either say leave it 0 and 2, but indicate that they're x values, in which case once you find an antiderivative, you have to switch back to x's. Then you can substitute in 0 to 2. Or you could do it the way that I did here, which is find the corresponding u values for these x's. So that's the way I decided to do it this time. If u is 0, if x is 0, what is u? So I plug in 0 here, like I did right here, and that works out to be 7. So that the lower limit becomes u is 7. That corresponds to x equals 0. So when u is 2, plug that in here for 2. Let's see, 2 to the 5th is 32 times 3. 96 plus 7 more is 103. And so that gives us the upper limit of u being 103. Now this has the advantage of not having to switch back to x's at the end. Of course, I did have to figure out what the u values were. So the power goes up 1 to negative 3. Multiply by the reciprocal of that power. Negative 1/3 times positive 1/3 is negative 1/9 here. And I could rewrite that as u to the 3rd. So I can leave the negative 1/9 out front, and I have 1 over u cubed going from 7 to 103. So it's 1 over 103 cubed minus 1 over 7 cubed times negative 1/9, which is like this. And the common denominator is just 7 cubed times 103 cubed. Okay, because those don't have a factor in common, which is multiplying these two denominators. And then you multiply top and bottom here by 343, top and bottom here by 1,092,727, which is 103 cubed. And of course, I probably did that on a calculator. And now you have a common denominator, so you just add the numerators. This one's positive, this one's negative. Two negatives here make a positive. And it looks like this top one must have 9 as a factor. You can see that by adding up the numerator, the digits. Let's see, 8 plus 4 is 12, 3 more is 15, 2 more is 17, 1 more is 18, and 9 is 27. Since that's a multiple of 9, that means 9 will divide into that evenly, and in fact it does, and you get 121,376. I think there's no other common factors in the numerator denominator here. If there were any, it would have to be some power of 3, 103 or 7. So you just check those and see they don't divide out. So that's reduced. And we could get a decimal approximation if we needed to. Here I did it on a CAS calculator, a TI Inspire CAS, and did the integral. Here's the exact values of fraction, which is exactly what we got here. And then I did an approximation on the calculator. Here it is to a lot more digits, but there it is to 4 decimal places. Graphically, what is this? We're going from 0 to 2, which is right here, and then going out to right here, and we're talking about an area under this curve, and that's what the curve looks like. Notice we had to zoom in pretty closely here. It's really small. So it's a really small area. Number 3, 4x over 36x squared plus 1. This is very similar to the last one in a way because I let u be the denominator. And the du then is the derivative. The derivative of 1 is 0. Then here I get 72x, and then I have my dx. So I can take the x and the dx and 72 together, and that becomes du. Then this, what's left is 1 over u. Then what else do we have? We have the 4's brought out front, and I put a 1 over 72 out front. That fraction reduces to 1/18. And so we have the antiderivative of 1 over u du. Well, the antiderivative of 1 over u is the natural logarithm of the absolute value of u. But then we need to plug back in what u is to get it back in terms of x, 36x squared plus 1. Notice that x squared is positive, then when you multiply by 36, positive or 0, and then you multiply by 36 and then add 1, you're at least 1. So that absolute value is not needed. We get to this right here. So the final answer is 1/18 times the natural logarithm of parentheses 36x squared plus 1, close parentheses, plus c. Again, here I did it on the CAS calculator, and that's what I got. Here's how you check it on a like a TI-84 calculator. Okay, you let number y2 be the numerical derivative of y1. That's a math 8 on the calculator. But the one you want to take the derivative of is the answer. So you put your answer right here in y1, put any number you want for the c, or just leave it off. And then for y3, put the original integrand, the thing you're integrating, 4x over 36x squared plus 1 right there. And y2 and y3 should have the same table, which you see right there that they do. So that's a way you can check it on that calculator. Notice that the TI-84 does not tell you the answer, but it will give you a it will check that antiderivative for you without telling you what it is. CAS calculator will just compute it for you. Number 4, it's almost the same thing, but I didn't put an x up there. The way we want to do this one is we want to see that 36x squared is 6x squared. So this time we let u be 6x, du is just 6 dx. We put a 6 here, we bring the 4 out front, divide by 6. 4, 6 is 2/3. And if you look at this, becomes 1 over u squared plus 1. The 6x is du, 2/3 is still out front. And when you recognize that as the derivative of an arctangent function, so this is 2/3 arctangent of u plus c is an antiderivative, it's the family of antiderivatives. And then, of course, we needed to switch the u back to x's to get 6x there for our final answer. The family of antiderivatives is 2/3 times arctangent of 6x plus c, and the plus c then, of course, for any real number c gives us an entire family of those antiderivatives, and that's exactly what this gives you here. Notice when you do the antiderivative here in the calculator, the CAS calculator, that's a T-inspired CAS, you do not get the plus c, so you have to remember to put that in there. It's just going to start with the c of 0 probably, and then it's using a different notation for the arctangent, but that's the same thing. Number 5, determine the antiderivative of tangent of 6x. So as the hint says, we want to change tangent of 6x to sine of 6x over cosine of 6x. If we let u be the denominator, cosine of 6x, then du is, that's like cosine of w, so you get minus sine of w times the derivative of w. So that turns out to be minus 6, or negative 6, sine of 6x times dx. Well, we pretty much got everything except for the negative 6. So you put a negative 6 here and a reciprocal negative 1/6 out front, and this works out right. So this becomes 1 over u, and all this right here becomes du. So notice that cosine of 6x is all sucked up inside that u, and everything in this parentheses is equivalent to du. So remember, this is the way substitution works on these integrals. You have to be careful that you take care of that du dx relationship to see what you have to substitute there. And it's usually not as easy as just du equals dx. So you have to take that into account. Well, then the antiderivative of 1 over u is the natural logarithm of the absolute value of u. So we get negative 1/6 natural log of the absolute value of u plus c. And then we substitute u in as cosine of 6x. Here we need the absolute value because the cosine can take on both positives and negatives. Now, I did something in the last step that's optional, you could do or not do. The negative 1 here I brought inside and made this into essentially into a power, and cosine to the negative 1 power is secant. So I have 1/6 the log of the absolute value of secant of 6x plus c. That's another way to write it. The calculator actually gave me the line before the last one for my answer. You could even say it's the log of the 6th root of secant of 6x if you wanted to. Leave out the 1/6. All right, let's keep going here. Number 6, a definite integral from 0 to the square root of pi over 4, 4x times sine of 3x squared. All right, let's let u be the 3x squared, trying to shoot for a sine of u. Du then becomes 6x dx. Okay, that's no problem. We got the x. We can get the 6x here. Put the 1/6 out front with the 4. 4 times 1/6 is 2/3. So that's what we have. If we rewrite it that way, then we can see that that's sine of u times du. Doing a definite integral, 2/3 out front. Now we need to change these to u values. Notice that u is 3x squared, so when x is 0, u is also 0, so the bottom limit didn't change. The top one does. X is the square root of pi over 4. Square that, you get pi over 4, and then times 3 is 3 pi over 4 for the upper limit. Now, the antiderivative sine of u is pretty easy. It's just cosine minus cosine of u, so it gets a minus out front. Cosine of u, and evaluate from 0 to 3 pi over 4. So it's cosine of 3 pi over 4 minus cosine of 0. Cosine of 0 is 1. Cosine of 3 pi over 4, that's one of our special angles. That's in the second quadrant, so the answer is negative, and it is 1 over the square root of 2, or square root of 2 over 2 for that special angle there. And I just distributed this and found a common denominator. Let's see, this is, let's see what we've got here. So when I distribute this, I have the 3 in the denominator. I'm going to distribute the negative 2. Negative 2, and this negative 2 cancels, leaves me the square root of 2, positive. And the negative 2 times the negative 1 gives me positive 2. So one way to write it as a single fraction is 2 plus the square root of 2 all over 3, and which rounds off to about 1.1381 as a decimal approximation. The exact value is the one with the square root in it, though. And that's what the CAS calculator gave me for an answer here, and a decimal there. Graphically, this is an area from 0 to pi over 4. We take this, and let me think about this a minute. 0, between 0 and pi over 4, this is 0 at 0, and then positive right after that. Eventually does come back down negative later on. But this is an entire area that's above the x-axis, so it all adds up to the integral. So this area between the curve and the x-axis from 0 to, what was it, square root of pi over 4, which is about here, that area right there is what we're talking about, and that's the exact value, or approximately that much. Number 7, evaluate the integral from 0 to 2 of e to the 5x dx. Let u be 5x, du is 5 dx. Put a 5 in here, put a 1/5 out front. It becomes e to the u du, 1/5 out front. We have to switch the x's to u's. So when x is 0, 5 times 0 is 0, so u is also 0. When x is 2, 5 times 2 is 10, so u is 10. So the antiderivative of the e to the u is e to the u. We just evaluate from 0 to 10, so it's e to the 10th minus e to the 0. E to the 0 is 1. So it's e to the 10th minus 1 over 5. That turns out to be approximately 4,405.0932. Again, there's the check on the TI Inspire CAS. And here's the illustration. We're talking about a graph like this. We're talking about the graph, the area between it and the x-axis. This is way up there in terms of numbers because it's zoomed way out in the terms of the vertical scale. Okay, let's do one more and then we'll break for a second video on these solutions. The integral from 1 to infinity of e to the negative 2x dx is an indefinite integral. Okay, I should have been saying all along, I should have really been making some notes here. I should have been saying the integrand is continuous over the interval, so we can apply the fundamental theorem of calculus. Okay, and really I should be putting that on every single one of these that I did a definite integral. That one, this one, and this one, because that is a requirement of the using the fundamental theorem of calculus? Well, that it's that the integral is continuous. The function that you're integrating is continuous there over that closed interval. But when we're looking at this one here, you're obviously not going to be closed. A closed interval going to infinity is not going to be continuous there because you can't really have a closed interval at infinity, not with real numbers anyway. So the way we do this is we replace infinity by some letter. I'm going to call it a, and then we take the limit of this as a goes to infinity. If that exists, then we can go ahead and find it. Now, this integrand now is continuous from 1 up to a for any real number a, so we can apply the fundamental theorem of calculus, and then we got to apply the limit at the end. So anyway, we're going to do a substitution. Let u be negative 2x, du is negative 2 dx. Put in a negative 2, put in a negative 1/2. Okay. And let's see what happens here. And we're going, this time I just said x equals 1 to x equals a and left it like that. E to the u derivative, antiderivative is e to the u. And we're going to go from x equals 1 to x equals a, so I have to switch back to x's. So it's e to the negative 2x from x equals 1 to a is e to the negative 2a minus e to the negative 2 times 1. Of course, that's just e to the negative 2. That's a variable a. And remember, all along the line, we've got the limit as a goes to infinity here. At some point right here, I took the negative 1/2, factored that out in front of the limit sign, or brought it out in front of the limit sign using one of our laws of limits. Provided this limit exists, that's cool. So now we take the limit as a goes to infinity. This part here is actually going to go to 0. And so we get, see, the two negatives make a positive. And since I already have fraction, and let me make this a positive exponent by putting the e square in the denominator. So it's 1 over 2e squared, or approximately 0.0677. And here you can see the CAS calculator giving me the same thing. And so what we're talking about now is something here, quite remarkably, has an infinite boundary along the bottom and the top, but has a finite, actually pretty small, finite area altogether. All right, let's stop here and we'll pick up the solutions to the next exercises, the rest of these exercises in this set on our next video.